Okay, so our first example is just going to be a real simple linear one in x and y. So suppose I'm doing a conversion from x and y to some u and v, where I can define x to be 3u plus 6v and y to be 9u plus 2v. I would want to know, what do I need to do that? And I'm sorry, everyone. I should have given you a little bit notation before. I got caught up in trying to explain what these things mean. The notation that you're going to see like in web work for how to calculate this quantity is going to be like derivative of x and y over derivative of u and v. So you'll be asked to calculate that quantity many times, but really what we're doing is we're just trying to find the conversion factor for dA. So to do this, I just take all my partial derivatives. So dx du is going to be 3. dx dv is going to be 6. dy du is 9. And dy dv is 2. So they're pretty simple derivatives because it's all like scalar multiples. And then I put them inside my Jacobian matrix. I'm just starting with the vertical bar because I know I'm going to want to take the determinant, but I put my uv this direction and my xy this direction. So I'm going to start with dx du, dx dv, then dy du, dy dv. And I just put in the numbers that I calculated for those partial derivatives. Remember from our example before, the partial derivative won't always be a number. Sometimes it can be a function of the other variables you have, but for the simple one it's not. So I'm going to have 3, 6, 9, 2. And then when I compute that determinant, I multiply the main diagonal. 3 times 2 is 6. And then I subtract the off diagonal. 9 times 6 is 54. So I'm going to get minus 48. Six minus 54, yeah, okay. So then my answer here would just be that quantity I'm looking for, d of xy over d of uv equals minus 48. Or if I was putting this into an integral, dx dy is going to be 48 du dv. And then that's just how we do this type of example. Oh no. I want to show you one that is still a 2x2, but showing it with functions now instead. So I am going to do that polar example. So my x is r cosine theta, my y is r sine theta. And I just want to show this example because it's going to look a little bit more complicated with the r's and thetas. Let me check where we're at with time. Yeah, I think I can finish this and like keep it under 10 minutes. Okay, so I'm just going to take all my partial derivatives. dx dr is cosine theta. dx d theta is derivative of cosine, which I always forget. Which one is negative? Derivative of cosine. I think that one's the one that makes it negative. Negative r sine theta. Then I'm going to do dy dr is sine theta. And dy d theta, would be r cosine theta, and I think that's the one that doesn't have a negative. And after I take all those partial derivatives, hopefully we're really comfortable with partial derivatives at this point in the semester, I put them inside my Jacobian. I'm going to do my dx dr, dx d theta, dy dr, dy d theta. And then I just put in all these functions and hope it gets simpler later. So I've got my cosine theta, my minus r sine theta, my sine theta, my r cosine theta. And to calculate the determinant, I multiply along the main diagonal. So I've got cosine theta times r cosine theta. And then I subtract and I multiply along the off diagonal. So I've got minus r sine theta, oh no, sine theta. And when I simplify this, I'm going to get r cosine squared theta, then the minus becomes a plus, r sine squared theta. Or I can pull out that common r, leave cosine squared theta plus sine squared theta inside. But we know cosine squared plus sine squared is 1, so that does just become r, which is exactly what we saw when we learned about polar coordinates at the start of sort of this group of chapters, which is that if we take dx dy, we're always going to have r dr d theta.